Let us go back to the session. Okay, welcome to the session on scriptless scripts and multi-party channels, which will be starting right now. And each talk would have 30 minutes discussion inclusive, so please pay attention to the timer for each presenter. The first talk will be given by Olaoluwa Osuntokun. Okay, right from Writing Lab. Okay, title will be multi-party channel. You have something?
No, you go ahead.
Okay.
Now I was going to ask a video to raise the frame speed to 120 FPS.
Okay. Multi-party channels in the UTXO model, challenges and opportunities. Okay, please start and please welcome that presenter.
Hey, my name is Olaoluwa Osuntokun. I am also known as Roast Beef. I'm CTO and co-founder of a company called Lightning Labs. We're working on some lightning stuff, things like that. I'm going to talk about kind of my talk's not really going to have any concrete rules. We're going to be kind of like a tour of kind of like some abstract things I think we can do as far as like multi-party channels. So I think it's a pretty cool area of research. Some people call it this kind of like science fiction, compared to like regular like single party channels. And I think there's maybe a lot of complexity in terms of like in the actual implementation of some of these things. But I think it's pretty cool to discuss, and maybe you can get a little more kind of a discussion going around it and like research revealing things like that. So I'll end my talk. First, we're going to talk about single party channels and kind of like what the promise I think of multi-party channels are. And so, right now we have like single party channels pretty widely deployed currently. so we have single party channels pretty widely deployed in Lightning and people using right now for payments, things like that, which I think is great. I'm going to talk about some differences in the UTXO model versus the account model. So like most of the other proposals I think for multi-party channels have been in the account model itself. But I think UTXO model is a little more interesting because it like has a bunch of different things as far as like flexibility. Also going to talk about like kind of like what I've seen out there as far as multi-party channels. Like so I'm not really presenting like a new construction. It's kind of like more building off like prior constructions, maybe adding some new things to them itself. And then finally I'm going to talk about some like new things that I think can be cool, some that relate to Lightning, some things are kind of like distinct from it. And then finally just like kind of some like open problems with multi-party channels themselves. So for starting, so we have like the regular single party channel, right? And single party channel basically create like an account abstraction over like regular UTXOs. And we have a few certain on-chain transactions. We have like on-chain, open, close, cooperative close, force close, and splice and splice out, which basically lets us kind of like move funds in and out of the channel without actually disrupting it, which is pretty cool. And we also kind of have like this kind of like rapid off-chain execution of updates between two participants. This is really cool, and we can do a lot of cool things with this as far as like HTLCs, because once we actually have HTLCs, we have hash time like contracts, which can let us basically kind of like bind different channels with HTLCs, and then we get the whole like network thingy, which is pretty cool, and people are using it now. And this is kind of like going beyond that. Maybe can also have some like networking effects as well. But then we get into the limitations of single party channels, right? So some limitations is that like even though you have like the magic of HTLC, which lets you like link to particular channels, you kind of have like restriction as far as the topology, right? So you need to do some kind of like upfront work to create kind of like a suitable topology depending on what you want to do. It's kind of like a problem. We have something in L&D called like Autopilot, which is trying to do this itself, and you can like use test out like application, things like that. And then the other thing is you aren't able to actually dynamically create new channels, right? Because so every single channel that you want to create actually has an on-chain transaction within the blockchain itself. And this can be an issue because you say, okay, how are we going to onboard like a million users, with one transaction per user? That's going to take a while, and maybe we won't scale with the UTXO set. Another bad thing about this is like each channel actually requires its own UTXO, and the other thing is that you can't really have like one person can't have their own UTXO in the world. I don't think that's really going to work, right? Just because of like database size and things like that. There can only be also so many UTXOs in the system because it gets harder and harder to verify. And well, I guess maybe you can have the whole accumulator thing, which kind of partially addresses that. But let's like ignore that for a second. So now we have multi-party channels, right? So multi-party channels is basically like generalization on two-party channels that basically allow end parties to actually communicate and actually have end-to-end interaction. And the other cool thing about this is like you don't really require a new UTXO for each channel, right? So I can have one UTXO that maybe has like 100 participants within that, which is like pretty good for scalability wise, because all of a sudden now it's like every single channel doesn't have to have its own UTXO, maybe even collapse existing channels into one UTXO, as maybe we'll see a little bit later in the presentation. The other cool thing about multi-party channels is that like when you're actually doing the fronting itself, it looks kind of like a multi-input sweep, right? So basically, if you can use like different techniques for multi-signature aggregation, you can allow like end-to-end signatures to be like one single signature. So as a result, in the blockchain, it looks like a regular like output. Maybe it's like a witness key hash, a regular pub key hash, but it actually is like a big multi-party channel, potentially like 100 people or so, right? And this is kind of like a loose diagram of one. The one prior one had basically a 2 of 2 signature. This one basically has 4 participants with Alice, Bob, Carol, and the new entrant into the competition, Rodrigo. So Rodrigo can send to these individuals, can also receive from these individuals as well, which is pretty cool because now he doesn't have to like open a new channel to actually communicate with them. The other cool thing about this, you can basically like kind of create these like co-located like economies. These economies are individuals maybe will be frequently transacting with each other, so it makes them for them to kind of be under the same channel, right? So the other cool thing about this is that like because they're not doing any like network level forwarding on like the greater network itself, they can communicate amongst themselves, and then so now that you can actually save on transaction fees, and we can also have like much lower latency. We can have like different guarantees as far as like if I'll be able to send to the participant or not. The other cool thing about this, you can actually have off-chain channel creation and destruction, right? So as I mentioned before, every single channel creation and destruction for like regular single-party channels requires a new on-chain transaction. Well, in this case, we can do them off-chain. So all of a sudden, that's like really, really cool because now we can dynamically create relationships in the off-chain setting between two participants, depending on the changing requirements, or they can change whatever we're doing. Another cool thing I'll talk about later, you kind of had like dynamic route creation in like Lightning itself, which is something I call like tunneling, which is pretty cool because you can basically dynamically create routes between two individuals and not have that on the blockchain itself. And these can also be kind of like ephemeral. They can come in and out, and depending on like exactly what you want to do within itself. I think there's a number of qualifications. One qualification I think is like kind of like an MMO gaming server. So imagine you basically have the entire economy of a game in a multiplayer channel, right? So maybe we're playing like World of Warcraft. I give you some gold. It's an update in a channel, right? It's not like on some like big global blockchain or like whatever else is going on. It's a channel that's super fast and people can actually audit it themselves. We can also have like kind of like more like P2P focused payment applications because now like I have like Square Cash and like that. And everyone's like in like a few multiplayer channels, and these channels can also be linked together as we'll talk about a little bit later. And final thing is like maybe like bill splitting or something like that once you remit or whatever, because now you can have different guarantees as far as you can send payments to them or not. So let's talk about like kind of differences between the UTXO model and the account model. So typically in the account model, you kind of like have like a single account, maybe has like a bunch of like virtual. So you have a single contract, has kind of like a bunch of different virtual accounts with them, and that's like pretty cool. We have seen some people kind of exploit this, make multiplayer channels on different account models. One of them is Plasma, which is basically kind of like a hierarchical sidechain that has like different kind of exit clauses whenever you want to like exit the chain, and that's kind of like a big deal because if you can't really exit the chain in a timely manner, there's a bunch of like liveness constraints. You may like potentially like lose money. Same thing with like Lightning as far as like CSV things like that. We also have something called NoCus. It's like a little bit newer, and basically like kind of creates like kind of like a bimodal like ledger. So you have like an on-chain account, they have an off-chain account. And periodically you sync these every like few blocks or so. So so they have these things called epochs, and before the epoch, your transaction actually isn't final yet. So you need to wait until the epoch for things to actually be final. And the difference between these two is like these typically require kind of like an operator, and maybe the operator sees somewhere all the transactions, maybe has certain kind of like assumptions as far as like what they're doing. They're like kind of like withholding data and things like that. And also with NoCus, every single transaction actually goes through the operator. So when you want to transfer these things to UTXO model, you have a few kind of obstacles. Some of which that seems to kind of like force hierarchical constructions, right? And the thing with hierarchical construction is that you didn't necessarily have like a larger on-chain footprint, right? So there's no longer like one transaction on chain, and maybe have like 10 or 5, each of them are nested. And because we have limited block size, this can cause issues as far as like mass exits, and like will you be able to get your money out in time, and will like the time like expire before you get all the everything onto the chain itself. And the other thing is that we kind of like typically have like limited scripting with UTXO models versus like account models. So maybe you won't be able to do more complex like fraud proofs or actually proof things like that, which can maybe restrict some of the design that we can actually put forward. But I think UTXO model has like a number of advantages. One of which is you can actually easily create contracts off chain, right? So like typically like in some of these account-based models, they have something called like counterfactual instantiation because typically you don't know the like address of a contract if you actually deploy it on chain. Therefore, you basically do a bunch of like kind of complex things with like account registry and things like that to actually be able to create new contracts and fly off chain. But with UTXO model, I can just like nest a new transaction. I can just have that there, and it's pretty easy because now I don't need anything else fancy. The one important thing is that like creating a new contract off chain, kind of like an SM will require something called sync hash no input, which was originally proposed in like Lightning paper, and like I wrote an implementation maybe back in like 2015 or so, but now it's back for L2, so maybe we can get that in. We can have a bunch of fun as far as like doing different nexus contracts in the UTXO model. And finally, the cool thing is that because the hierarchical model, like you don't really have like one like primary operator that's like doing all the different transactions. So you can kind of have like more kind of like loosely coupled form of it, where I can be doing like updates in some subtree, and then maybe if you're in another subtree, you don't really know about what I'm doing, which I think is tight. So let's talk about a little bit kind of like lineage of multiple channels, the way that I'm looking at it right now, right? So initially there's something called Duplex channels provided by C. Decker and like Wattenhaver, some other people at ETH University. And basically what this did, it made like bidirectional channels by this kind of like nested time lock and validation thing, right? So you basically like have a series of like Decker time locks, and the idea is that like the most latest state can only be published before, and the newest state is that it would be published before like the prior state. And they did this like pretty cool construction where you kind of like had this construction where like you had like you recursively applied this technique to basically allow the channels to last a little bit longer. And like more recently, they added something called kickoff transaction. So the prior version of this only had like a finite lifetime, but then they added something kickoff transaction which used relative CSV to actually start the clock ticking, right? So before this, maybe you had like 10 days or whatever else to do it, but then they extended it and it went even beyond that. And then something else recently, I guess this was dropped this year, something called L2. So like typically for Lightning, like you actually, or we call it like for Lightning, right now other things like that too. You have something called like replacement by revocation, which means every single time you make a new state, you basically revoke the old state, right? But L2 has something something else which is kind of different, where they call replacement by version, because now I basically have like incrementing versions, and the best version is the final version. And so like there's different kind of like trade-offs between the two, because like for L2 you can say that like I can always like publish a prior state because there's no actual punishment for me, right? And the revocations have like a different state. Me myself, I like revocations. I think maybe you combine them somehow, well, which would be cool though. But the cool thing about L2 is that like it allows you to kind of like avoid an issue with this thing called channel factories. That's kind of like a larger state blow-up because you have invalidation trees. So already you kind of have like a very like nested subtree of a bunch of commitments. And you also have to have like a invalidation tree for each of the kind of like allocations that can add a lot of state. And instead L2 can help us get rid of that, which is pretty cool, I think. So originally like something called channel factories was kind of like a framework for hierarchical frameworks. It was a framework for hierarchical channels within the UTXO model. So you basically have like a series of like commitment transactions. They're kind of like Vienna. You can have a bunch of different commitments and things like off of that. So originally using validation trees for these end-party commitments, but now we can use L2, which is really cool because we can simplify it a lot. We can kind of eliminate a lot of like on-chain state blow-up and do things in a different fashion itself instead. And there's something else that's recently published. I haven't like really got all the way through. It's called like lightning factories. And one thing it tries to use is like it tries to like do a channel factory light construction in the revocation model, right? So previously, like in the revocation model, there's kind of some issues as far as like a state blow up because you kind of have like end parties. Each of the end parties have end states. They can publish any of those end states, and then even from that, any of those like n-1 parties can publish an end states or n-1 states and so on. But this kind of like has like different framework to maybe solve this problem that I shouted out. And there's like kind of new. It also uses BLS signature to actually kind of like solve some of this interaction issues because now you have like and you have linear communication of n-square communication, but it doesn't spiritually solve the state blow-up issues. But let's go over kind of like channel factories because like everything I'm going to be talking about actually builds off channel factories. I call them kind of multi-party channels, but they're the same thing more or less, right? So what they are more or less, they are a series of kind of like layered commitment transactions. So rather like typically channels you have like something on the blockchain, and then you have like one layer bit below that, and you have the commitment transaction. You can use that to actually update your balance. And you can broadcast that, and that'd be final. But channel factories, they kind of like have these like layered constructions and stuff. So the first thing is called a hook. So the hook is the initial n of that multisig, right? So like let's say we have five participants, rather than like a 2 of 2 on the chain, we have an n of n, right? So the thing is, anytime we want to modify what spends directly from the hook, we need to have all n participants sign off from the channel itself. Then we have the allocation. Oh yeah, you can actually make that single key, which is pretty cool. Then we have the allocation. So the allocation spends the hook itself and then goes into like smaller commitments or allocations from that. So you can imagine we have like 8 parties in the hook, and then we have an allocation. Maybe we have like 2 fanning out, and then we have like 4 of 4, and then we go down a little further, and then we have like 2 and 2. So you can kind of like use this in pretty cool composition, like mix and match them in order to actually create kind of like a construction that works for you and where you want to work on. And finally, we have the commitment, right? So the commitment are typically the leaf nodes. Usually these are 2-party channels, but they can actually be multi-party channels beyond things like that. And here is next. Here's like a picture of what this looks like. So you have like the hook and the section from the original paper of channel factories itself. You have the hook that goes to the end of a multisig, and you have like allocations. In this case, we split them up into like 3 different allocations of 2 multisigs each, and then from there we can go to different commitments, right? So this is kind of the general structure. And you can see here that like if I'm over here, like I'm like the yellow one at the bottom left, I don't really know who's being updated on the top right and things like that, right? But because I'm here and here, I can actually maybe do like an HL CPT myself, as we'll see a little bit later. So let's talk about some new stuff now. So like I was kind of covered like the way channel factories work and kind of like their structure and the model. Now we're getting some like new ideas of like what we can do, things like that. So one cool thing with channel factories, you can actually do off-chain channel creation, right? So one question people have with me Lightning all the time is like, okay, if I have like a new user Alice, how do we get Alice onto Lightning without actually having a new on-chain transaction, right? So typically, there's different ways we can do it. Some we call like sidecars and things like that. But like this can actually let us make a new channel without going on-chain at all. So the cool thing here is that because we have the hierarchical channel, we basically just make a new key and make a new commitment in this nested subtree itself, and that requires no on-chain transactions. The downside of this obviously is that like because we can't modify the hook, we can't actually add a new multisig into the hook itself. So it has a kind of like a different trust model, but it's kind of like in between like a custodial model and kind of like like a weak subjectivity model and kind of like a further trust model. But I think you can still do like cool things with that. And the cool thing about this is now once the user is in the tree, they can update the channel, they can receive funds, they can do anything else that they want. So all of a sudden we can basically have like a bootstrap, maybe with like 100 participants that actually have this channel factory on the chain, and from there we can add new participants from there on. Which I think is pretty cool. And the cool thing here is now we don't really worry about the UTXO set size because we can have like potential thousands of participants, maybe thousands is way too much, maybe hundreds, in single UTXO. But this is a little bit different because it requires like a new trust assumption, right? So the question is like when Alice actually joins this new channel, how does she know that this is like the most valid state, right? So let's say I paid someone like $5 and they got me into like new multiplayer channel. How do I actually know this is the most valid state? The thing is, if this is not the most valid state, then I basically like lost money, right? Because if I try to publish my commitment, it's revoked and I would lose all the money itself. So instead, we basically need to have something I call kind of like a channel audit proof, where you basically prove to me the existence of the channel within the the multiparty tree itself. So I need to get this proof from like the leaf where I'm going to be added to all the way up to the root. The thing is like every single like multisig that we run into into, there's kind of like a threshold question there, right? Like, how many parties am I going to get to attest to the state? The thing is, like, if all the parties lie to me, I can basically, accept like a prior state that maybe doesn't actually exist. But if I have some like threshold assumption, maybe I have like 2/3, or maybe like I have 50% of them, I can actually trust them and then say, okay, this is actually the real state, and I can go from there on. But it's a new kind of like assumption. It's kind of like, is there a thing? Yeah, it's kind of like weak subjectivity in proof of stake, because it's kind of like, okay, who am I trusting to know what the latest state is, right? Or for me to actually bootstrap into this new network. The thing is, like, the considerations are actually like much lower, because like, if they lie to me on this, like, it's not like root blockchain security. It's kind of like, okay, well, I lost my $5 to enter Lightning. Maybe I'll actually just go on chain now, and maybe someone can subsidize it. That's cool. Another cool thing that we can do with off-chain transaction, we can like now splice in new participants, from the hook transaction itself. And one key thing we actually require to take no input for this, right? Because if we modify the root allocation, every single without no input, that changes the root TXID, right? Which means every other transaction in that entire tree is now invalidated, right? But if we can actually now use no input, which is maybe doesn't even sign the script, only just like goes for word satisfiability, all of a sudden we can now add and remove new people from the channel. Maybe this is like an exchange withdraw and deposit. Maybe it's like some people like enter or leave from the game without disrupting everybody else. And this is also cool because now I can also add and remove participants from any of the hook allocations without disrupting any of the subsequent channel nodes within the tree itself. Next. Yeah, did I go over this? Auto proof. Oh yeah. So with the auto proof itself, like you actually require them to like fully prove the existence of every single channel within the tree from the leaf to the root. And one thing here is like obviously if the threshold of them possibly or even all of them 100% gave me the actual signatures for all of them, I could broadcast that on chain, right? I could kind of disrupt them. So instead we do rather than using like double SHA in the stake hash, we do a single SHA. And this is cool because now all of a sudden I can kind of like know that okay, with some degree of trust assumptions, I know that this is the latest state. This is cool because anytime I want to do anything like create a new off-chain channel or even swap between different channels, I would get one of these proofs, and using these proofs I can then go and then decide okay, this is actually legitimate, I can go forward, which I think is pretty cool. Another thing we can do is basically route tunneling over Lightning, right? So right now, like on Lightning, like it uses kind of like a circuit switch graph, and because of that, like the graph's like relatively static. Because anytime you want to like open and close a channel, that actually is an on-chain transaction, right? Channels can take up to 6 confirmations to actually be advertised to networks to be fully routable. Also, we have like 10-minute block time, which maybe can be 30 minutes or 100 or an hour or whatever else beyond that. And the other thing, also like there's a little bit of strain on the nodes themselves if you like client or a full node, because you actually need to verify the channels actually exist to ensure that no one's giving you like a fake graph itself. Another cool thing is that you can actually now do dynamic route creation, right? So you can imagine maybe I have like Alice, Bob, Carol, Dave, and then like typically maybe I'd go like a 3 or 4 hop path over to Dave. But what if Bob and Dave were in the same multi-party channel, right? So all of a sudden I can tunnel from Bob to Dave instantly without actually having any new transactions. So it's like they're kind of like another dimension. Maybe it's like kind of like an underworld, like lower thing, or it's like like the middle world or something like that. And I can like tunnel through them into the upper dimension, which is like I guess real Earth. The cool thing here is that I can actually now like dynamically create and delete channels based on the directional flow within the network itself. So like typically, let's say someone wants to open a new channel to like satisfy a new merchant because maybe the liquidity wasn't sufficient to route to like the new store that's selling like stickers or whatever people are doing these days. That potentially takes like an hour plus for me to actually advertise the channels in the network. But instead of using this, I can basically do that in seconds, right? Assuming that I have some like path within this like hypergraph over to that new merchant, which I think is pretty cool. Kind of like changes the game. The other cool thing with this is that you can kind of like really reimagine like routing with the network itself in these like multi-party channels and sub-channels. Because what you do is that like I would create these new new advertisement, but it's right. Like so right now in Lightning we use kind of like a circuit switch network, right? Which means like I actually use source routing, I know the entire graph. For this you kind of require something more distant vector-like, kind of like the traditional internet, where I basically like show like, hey, I have a path to Dave, via Bob, who can route through me. I don't really know that's going to work, but I can maybe try like a smaller amount if it gets over there. Maybe I can do a circular route. I can know that okay, maybe that's going to be legitimate. And the other cool things, I think maybe you can supplement this with some things that have been recently proposed for kind of like congestion-aware packet switching protocols within the network itself. So right now, it's like whenever I'm routing, I don't really know like where the best flow is. But some people propose some new algorithms, which basically allows us to like at every single packet switching level, basically go in the direction of the least congestion within the network. The cool thing about these proposals, they actually like actively balance the network as you're routing through them. People would talk about rebalancing and like how that's really important, like they want to write scripts, things like that. If we go with this route, that could possibly allow us to do it like just by sending payments, which I think is a pretty cool thing itself. The other cool thing is you can actually use it as a bridge to multiple channels, right? So let's say we have like 50 or 25 people per channel, we can all of a sudden like link every single one of these channels within the network itself by just having like a few bridges. And these bridges can also be dynamically reallocated and actually also remade within themselves. So all of a sudden like now like paths like they're in your imagination because you can maybe create a new one at any given time. Just kind of like bootstrapping based off like an upper layer which you can actually validate and then go through from there. Route tunneling. Multi-party nodes, yeah. So the alternative, like, you can actually have now like multiple people in a single channel, right? So like maybe I have like 20 nodes, and 20 nodes are now under like one pub key within the network, and they're using that to combine liquidity within the network itself, which is pretty cool. The cool thing with this, you can now aggregate these channels. So before we were kind of like using these like advertisements, where I could say, okay, 10 people have routes to the other 10 people. Instead, I can just like coalesce all the advertisements into like one particular node. And the cool thing about this, you can actually now kind of like combine all your liquidity within one particular channel. So maybe like we didn't have enough money for like 20 BTC channel. If 5 of them get together and have one 20 BTC channel, maybe that can help the network to route additional payments. One thing that actually, it's cool because it actually shrinks the size of the public graph. Rather than like, you have like 100 different nodes in the multiplayer channel, I basically have like one mega node that can use that node to route payments actively. One other thing within network right now, we actually have a limited number of down ACLCs within a convention transaction. We do this in order to ensure that we can actually like sweep a single, I can do a verification of all the ACLCs in the convention transaction in one transaction, but we can actually increase that a little bit, and we can increase that to it's like in the thousands, and like low thousands or so, if you actually respect the max policy weight limit, and that's right now. I think it's 400,000 weight or so. One thing that's in place is like we have something called AMP, which like lets you kind of like split payments with the network itself. And so if you have like if we have like more HTLCs, we're doing more sharded payments. There's only a limited number of commitment space in the transaction network wide. You're gonna have like this kind of like strain on the number of like available queuing slots you can say in the network itself. But what we can do, we can actually like use these channels, multiplayer channels, to like continually add like newer convention transaction nested within the larger channel. So it's kind of like a file system where you have like an inode. The inode maybe has like a direct block, which is like a like 4K or something like that. Then you can have like an indirect block. And the indirect block points to like more blocks and more blocks. You can basically like fan this out and like have more space within the network. You can do this for similar commitments as well, but I think it kind of works a little bit. You take regular channels. I think it works better with multi-layer multiplayer channels. The other thing is like, let's say like I want to do receive and open this multiplayer node, right? So we have like 25 people, and those 25 people have like one particular pub key. How do I send a payment to any of these nodes in that channel itself? So one thing we can do, we can basically use the thing is kind of like a hierarchical prefix address, right? So what we do is like when we're sending a payment to this node, rather than just like addressing it to like the node and their pub key, we use something it's like in Lightning right now we have these like onion blobs, right? And with the onion blobs you can add additional data. We call them extra onion blobs. What I can do is I can basically add another address into this onion blob, which helps me actually dispatch the payment once I get to that mega node. So what we can do is based on the kind of like structure of the tree, I can like have like a prefix address that would address to which particular node I want to route to. So like let's say it's like a binary tree. I say okay, left right, and I can go to like the 8th node, and I can use that to actually route a payment within these participants, which is cool. Another thing we can do these things kind of like cross-channel swaps, right? So like let's say like I'm in a different subtree and you're in another subtree. Maybe we want to like swap coins. Maybe they're the same. Maybe they're different coins. Or maybe we're even doing a cross-channel swap. And maybe because like I don't like these participants over here because they're playing like the new expansion pack or WoW, and we're getting that. I can go over there. So typically, there's kind of like some issues with like regular atomic swaps, in that you kind of have like this free option thing. And like once we actually do this setup and we have all the transactions all laid out, I can like just kind of like defer execution, or I can just like I can wait the entire time. And then we don't want this to happen because we want to ensure that everything is actually like timely. We want to avoid this like kind of like withholding problem which also exists for regular atomic swaps. So that we're going to use atomic swaption. So atomic swaption is basically a option to do a atomic swap. Like I didn't make this as like bunch of people like was like made this in like mailings and things like that. But what it is more or less typically on a regular swap, you basically have like one secret, right? But instead now like Alice sells Bob or whichever, Alice sells Bob the option to actually do the swap themselves. So the difference is now we have two secrets, right? The first secret is kind of like the acceptance layer. So basically once Alice buys this, or I guess Bob buys the swap, Bob can actually now like just wait. Because now at this point, like Alice has already been compensated. So at this point, like Bob paid the premium to actually enter the swap, and then now he's like been compensated. So it doesn't really matter. He can go forward with it itself. And then we have the final exercise layer, and then Bob can actually go through and reveal secret B to go through. So this is pretty cool because you can basically do a swaption for like anything, like swaps, channel acceptance, whatever else what you want. And one other kind of like solution I think for this problem is that you can do kind of like a more like a microtransaction where I can send like one search each time. I can like ratchet that up. Maybe if you don't like that, and maybe that adds a lot more communication. But instead you can do swaption, and you can get paid for the premium of the cost there. Other cool thing, this kind of like potentially allows like for someone to like sell a channel within another point channel itself. So I can potentially like maybe through different things like submarine swap, I can like push all my funds out onto on chain, and then sell this channel within the multiple channels directly to you using something like a swaption. Moving on, channel orchestration server. So the vanilla version of this kind of like requires like end-to-end communication with other participants. It's literally like one giant like multi-party computation, right? And we know it doesn't really scale well. What we can do, we can basically add like a server with that just does purely message passing, right? So all the server does is it has like a series of mailboxes doing message passing between other participants to ensure that we can actually have linear communication rather than quadratic communication. And so the server kind of like acts as a rendezvous point between all these participants. Maybe it can be Tor or it could be something over else. But one thing here is like the server actually leaks timing information, right? Because now I can know that okay, maybe they didn't have the particular time. What we can do instead, we can have it went too bad. Okay. What we can do instead, we can add like W messages, kind of like a mix set to ensure that the server doesn't really know when I'm doing a real payment. So I can like continue to send something in a mailbox. Extension of this, we can actually maybe kind of do like an offline payment thing. So what we can do is we can treat the server themselves as like an offline mailbox. So all of a sudden we can pay the server to store this piece of a message. Maybe I'm doing like a multi-hop HTLC within the multiple channel itself. This is cool because typically like people kind of like complain they can't really do offline payments with Lightning itself. This lets you do them kind of because like someone has to be offline at a particular moment, but not everyone needs to be online at the same time. In the case of like like ads or settles themselves. So it's typically in the ad phase, if someone isn't online after a particular deadline, you can cancel it back. In startup phase, only the receiver needs to be online to actually pull things forward. Similar things popular over the regular network, but now you need to pay a bunch of participants to hold the HLC for a longer period of time, which may be not ideal. Some more problems. So one problem is like, how do we actually reduce the on-chain footprint to these max exits, right? So you can imagine if we have like 100 participants in the channel and they all want to broadcast at once. Now listen, we maybe have like 1,000 channels on-chain. How do we kind of reduce that size of that? Other question is basically, how do we allow someone to update the hook transaction without all the parties involved? Plasma kind of does this in that has like these exit games that works with, but Bitcoin scripting isn't really that's suffocated to do something like that. Could we have another way? Maybe something Taproot, Magical, Groot. Maybe we can get something in there and see what it does right there. Another question, like how do you actually do properly like health checking protocols, right? So the thing is that with this, you kind of like have like a bunch of like liveness constraints for all participants in the channel. If I want to update an allocation, you're not there, like I can't really do anything at that point. So we need to have like a way to efficiently figure out if someone is inactive and to ensure that we can actually do the update and slice them out in a reasonable time. Another thing is like how do we actually have like a language to kind of express all these like complex like allocations and swaps and swaptions and things like that? Because right now it's like you could do it, but you basically have to like manually code every single one of them. So it'd be very cool. We can have like kind of like a high level language where we can kind of combine down to like this execution or something like that. Something that I've seen that maybe you could work. This is something called a BitML, provided with academics in Italy, and kind of has like a pretty cool high level language that actually compiles down to transactions and scripts, right? So typically we have like language that maybe they do like script templating. This gives you the full transaction execution tree, which is something that you need for a construction like this, which I think is pretty cool. The other thing is like how do we actually do execution of time locks fees and time locks in the packet switcher model? Because typically right now with Lightning, because of circuit switch, we can basically know that I'm paying the exact fee to every single one of these individuals. With packet switch, I basically have to like send 10 satoshis, that didn't work, 15 satoshis, that didn't work, 20 satoshis, that didn't work. The thing is that with that can become very inefficient because you don't really know if your payment's going to work or not, and you may end up paying the max fee every single time, which is kind of like not really ideal compared to like when you're going to pay one satoshi fee. And that's everything. I don't have any questions.
Thank you very much. Okay, please come to the questions. Okay, go ahead.
Hi, thanks for the talk. I had a question about the routing protocol and how it's affected by this. Like you were saying, like tunneling through the multi-party channel to like update the channels via kind of like a state system that's outside of the routing network.
Yeah, so it's like a shadow route. I can basically like make like a shortcut. I can it's like a wormhole, I guess. I don't know.
So since currently the way at least I understand LND doing routing is it has kind of a mental map of the whole routing network.
Yeah.
And if I try to route and while I'm routing, it turns out this channel and this channel were like in a wormhole multi-party channel loop, and all of a sudden this guy doesn't have enough balance anymore. Mm-hmm. Would the number of payment failures increase due to this, or would there be a way to optimize to decrease or not increase the failure rate?
I guess you could say it's the same. I guess maybe they would increase if people were like lying about these actual advertisements. Because right now, we actually verify every single channel within the graph, so we can actually verify that multi they can sign with them. In this case, it's kind of like, hey, I have a route, maybe we should try it out. But it's kind of like an open problem because no one's really implemented it in practice. And we have like over a year now, I guess, of Lightning experience because we can judge how a current circuit switch model works. But yeah, maybe it would work, but I'm not really sure because no one's actually implemented it yet.
Okay, thank you.
Cool, thank you.
Okay, thank you. Some others? Okay. Then you will have some.
Can Ali Bakeverdi identify yourself? All right, thank you.
Thank you, Miss. Okay. Do you have one more question? Okay, if not, then let's thank the speaker again.
Okay, thank you.
Yeah. Now we are going back on the scheduled time. And second talk will be given by Giulio first? Pedro? Okay. And this work is co-authored by some other researchers in different universities. And the title of the talk is, okay. You start from the security and privacy interoperability in payment channel networks, which is a little bit shorter than the displayed one. Okay, let's welcome the speaker.
Okay. Thank you. So yes, my name is Pedro Moreno-Sanchez, and I promise I will talk a bit slower this time. Today I'm going to talk about security, privacy, interoperability in payment channel networks, and this is a joint work with my colleagues Giulio Malavolta, Clara Schneidewind, Aniket, and Matteo Maffei, who is in the audience today. We are scaling Bitcoin, so probably it's not a surprise, actually, that there is a scalability issue in Bitcoin, actually in cryptocurrencies. So the permissionless nature of cryptocurrencies make the transaction throughput really small. So we have a throughput of tens of transactions, give or take, which is not enough. And as you can imagine, this problem is only prone to become worse when we have more users and, more importantly, more transactions. So we have been working, the community have been working in several solutions, several approaches, and we can basically group them in two big groups. One is on-chain solutions, layer 1, sharding, there are many names for that. And the second direction is what is called off-chain payment channels, so layer 2 solutions. And this is going to be the focus of what I'm going to talk to you today here. So I'm pretty sure most of you may know the payment channels, but just in case that somebody doesn't know, the idea is that we have two users, Alice and Bob, and imagine for the sake of the example that Alice wants to buy books every now and then. What Alice can do is just perform an on-chain transaction every time, but as we have seen, there is might not be enough throughput for that in the blockchain. So what she can do is actually open a payment channel with Bob. And the whole magic of a payment channel is really like a multi-sig address between Alice and Bob, which contains the two public keys of them. So she deposits the coins there, and now Alice and Bob knows that these coins can only be sent somewhere else when they both agree. And as a fallback, there is this time lock mechanism, such that if they don't achieve such an agreement, the coins go back to Alice. And now when such deposit is settled, now Alice can actually start paying for Bob for the books. Let's say that a book is worth 1 Bitcoin, so probably is the most expensive book ever. But what she does is she performs a transaction from the deposit. She gives one coin to Bob and one coin to Alice. What she does is she signs it herself. And now Bob is happy because the only thing that he has to do actually is sign with his own signing key. So he knows that he can always do that. But instead of putting it on the blockchain, Bob waits for receiving more payments from Alice. So Alice can keep doing that. And she increases the amount of coins that she gives to Bob. In this case, 2 and 3, 4, and 5. And the moment is like at some moment Bob might want to get his coins from the channel. So the only thing that he has to do is take the transaction, sign it himself, and put it in chain. In that manner, the payment channel is closed. If you think about it, then the natural way to go forward is what if we have a network? What if we want to pay to several people around the world? So the naive way would be that we open a channel to everybody else in the world, but this is fairly expensive. So we need to lock coins in the channels. So we will have coins to create a few channels with our friends, but not with everybody. So the idea of the payment channel network is try to reach a receiver using the few open channels that we open, and hope that there are other payment channels that we can use as intermediaries in the payment. So as an example, so imagine that Alice wants to pay to the cat, but she doesn't have a channel with the cat, so probably Alice will find a path through Bob to reach the cat. And this is the main notion, the main idea of the payment channel network, and this is how implemented in practice. So we have examples in Bitcoin and altcoins. So this is examples of Lightning Network, another implementation called C Lightning, Clara. There's also an example in Ethereum. It's called the Lightning Network. And I firmly believe that eventually any cryptocurrency will need, or any blockchain actually will need a scalability solution when the number of users and transactions go to a bigger number. So in this state of affairs, let me use 1 minute to do publicity of what we do in our group. So basically what we're interested on is trying to look at the formal definitions of security, privacy, concurrency. And for that we use a trick in cryptography which is called Universal Composability Framework. Once we have these formal definitions, we are interested on whether these current implementations, current Lightning Network, or current implementations that we have in practice achieve these security and privacy definitions. Actually, in recent work, we have shown actually that there is an inherent trade-off between privacy and concurrency, which in practice means that a payment channel network cannot achieve a strong privacy or strong privacy guarantees and strong concurrency guarantees at the same time. And again, once we studied the current network, we would like to provide cryptographic constructions that work in practice, and we also show that they have formal security and privacy guarantees. And in a moment, in the rest of the talk, you will see what I mean by that. So let's start with security. And security is a broad term, so I think the first thing that we should do is agree on what we mean by security. What's the notion of security? In our work, we define security as balance security, and intuitively means that obviously the honest users that are used as intermediaries in a path should not lose coins in a process. A bit more formal means that if Bob is part of a payment and he has a balance of 10 coins, it should not be the case that after the payment, Bob has less coins than before. Or a bit more formally, the probability that this case happens should be negligible, should be really, really unlikely. So the Lightning Network is using a scripting language, a script part, which is called STLC, has time lock contract, to achieve this security notion in practice. And the idea is that now Alice can perform a payment in a payment channel to Bob, conditioned on the fact that Bob learns the pre-image of a hash function, which is assumed in practice to be hard. And following the example before, Alice can create the STLC to Bob, and that means that Alice not only signs the coin to Bob, but also attach a condition such that Bob now needs not only to sign, but also come up with a value x in these question marks, such that now the hash of x goes to this value y. And only when he manages to do both things, he can receive the coins. And this is pretty much the main building block that we have in the Lightning Network today. And the idea is that we can chain several of these hash time locks to perform a payment with several intermediaries in a secure manner. How it works in an example is depicted here. So imagine that the cat can think on his own a value x, and also the hash of that value x, y, and give the value y to Alice. Now what happens is that Alice can send the conditional payment to Bob, conditioned on the value y, and now Bob will forward that conditioned on the same value y to the cat. And this is because for Bob is okay, so he knows that as soon as the cat will reveal the condition, let's say the pre-image of the value y, he can always take that precondition and use it to get the money from Alice. So he's happy with that. Another important aspect here is the concept of transaction fee. So as you see there, or if you have noticed, Alice gives commits 1.1 coin to Bob, but Bob only forwards 1 coin to the cat. And this is because the 0.1 coin difference is charged by Bob as transaction fee, as providing the service of being an intermediary. This is really important because it's one of the main motivations that the nodes have in the Lightning Network to participate as intermediaries of the payment. Once the payment is actually logged from the Alice to Bob, then we go into the release phase in which the cat pretty much just reveals the value x, or give it to Bob, and then Bob, as I said, can give it back to Alice. And this seems like a secure construction in practice, but we looked into it a bit more in detail, and we came up with what we call a novel wormhole attack. So the idea is that the intermediaries in the path can collide to each other and prevent the honest users from the successful completion of the path. And the idea is that doing that, they can steal the transaction fees from the honest users. Let me explain that through the example. So imagine a setting in which Alice wants to pay to the cat, and Alice has settled all the hash time lock contracts already. So the lock part of the payment is actually done. Now what can happen is that cat gives the condition X to the intermediary, to the adversary, because cats want to get the coins, that's fine. But now what the adversary can do, instead of giving it to Bob, he can tell Bob, look, the payment actually failed, so forget about it. For Bob, it's okay, so just the payment fails, so he will just act as the cat, for example, refused to have the payment. Actually, the payment failed. But the adversary knows that the Alice actually at the other side of the payment is waiting for the same condition. So he can always get the condition and forward it to Alice as well. And if you see here, for Alice, the payment actually has succeed. For cat, the payment has succeeded, but for the intermediary, it seems like the payment has failed. And in practice, this means that the adversary gains coins. So if you see in this example, the adversary gets 1.3 coins from Alice, and he has to forward only 1 coin to the cat. So practice means that he got 0.3 coins, which means 0.2 fees for he being part of the path, which is okay because he was actually intermediary, but he also gets the fee from Bob. in this example. And as you can imagine, you can generalize this attack. So, and the main problem here is that really the same condition, the same hash value, the same y is used in the whole path. And as you can imagine, the more intermediaries there are between the adversary, the more fees the adversary can gain. And as I said, I think it's important because fees are the base for Lightning Network, for the payment channel networks in general, because that's the main motivation that the intermediary users have to be participants in the payment channel network. Another important point is that if you see here, from the point of view of Bob, he believes that the payment was failed, and there is no trace that he can use to claim that the adversary did something wrong. So for him, it looks like the payment failed, and it seems like a totally normal payment that just didn't succeed. Now that we have seen about privacy, we might also look at what we mean by privacy. What about privacy in the Lightning Network? And as we saw this morning, privacy is a big concept, and it's really, really important, as Ian mentioned this morning. So one thing that we should probably do first is like, what do we mean by privacy in this setting, in the setting of Lightning on the payment channel network? And in our work, we define privacy intuitively as the notion of relationship anonymity, which is similar to the notion of relationship anonymity in Tor network, for those of you that know that. And the idea is that an adversary who is sitting in the middle of the path should not know or should not be able to figure out who is paying to whom in a whole payment. So in this example, if we have two Alices or two senders and two receivers, the probability that the attacker actually thinks that the blue Alice is paying to the blue cat should be similar to the probability that the attacker thinks that the blue Alice is paying to the green cat. And this in practice means that the attacker doesn't really have much more information from the payment itself. So the only thing that he can do is actually guess who is paying to whom, who, by the way, he can always do. So then we studied, when we have our privacy notion, we studied whether the current PCNs, so the current payment channel networks, achieve this notion. And the answer, unfortunately is no, and the reason is basically the same as before. So we use as we saw, we use the same condition among the path. So the adversary sees that he gets a condition Y from the blue Alice there, and he forwards the same condition Y to the blue cat. So he knows that both of them are actually being part of the same payment. So he can link them together. And the same manner, he can use the condition Y prime to link the fact that the green Alice actually is playing to the green cat. And again, it's really problematic. See, having this same condition in all the hops in the path is problematic for security, it's problematic for privacy, and there are also other practical matters that we should look into. The idea is that we have some scalability issues in the sense that the way we build payment channels today requires a lot of information, or information that might seem not useful or not really necessary, as we will see. For example, to open the channel has two keys that define the two participants that are in the channel. The conditional payment also requires a script that has to be attached to the output, which puts the condition of the payment itself. And this is our variable bytes that we are using to put this into the blockchain. We also have privacy issues with this definition of payment channels, because as you can see, everybody can see that Alice and Bob, or the public key of Alice and the public key of Bob, are part of the same channel. So that reveals that they are actually operating a channel, which in practice means that they have business together. And these also have interoperability issues, which in practice means that any system that wants to use this definition of payment channel network must support the same hash function. So the same hash function should be used across all the blockchains. So in summary from this part, I think the payment channel network is a fantastic technology, but there is a long way to go. And there are several things that we need to work on and we need to improve. So we saw that the security is not as best as we would think of, or we would wish. The privacy also has problems. So we saw the attacker can figure out who pays to whom. And as we saw, there is interoperability issues, and also the transaction size is not as small as we would wish in practice. So in the second part of the talk, I'm gonna try to present what we propose to solve some of these problems. So the way we look into this is that, okay, transactions have signatures anyway, plus something else, plus scripts and so on. So, but the scripts are mandatory or are really necessary to authorize the payment right now. So what we can do with them? Can we do something more than just using the signatures for authorization? And thinking about that, we came up with this paper from Linder in 2017, and he explained how two parties can use the ECDSA protocol to come up with a signature, jointly between Alice and Bob on a given message, let's say a transaction or payment channel transaction. Says that it requires that both participate, means that requires the knowledge of the secret key from Alice and the secret key of Bob. And the interesting point here is that such signature can be publicly verifiable under a single public key, which can be constructed as the combination of the public keys from Alice and Bob. But in practice, we need only one public key to verify the final signature. This has some advantages in practice. So, for example, if you think of the open channel transaction, as we saw before we had two public keys to define the channel. Now we need a single public key to define the channel, which let us win some bytes in the transaction itself. Similarly for off-chain payments, right? So in the off-chain payment, we have to decide, we have to put the deposit, the multisig, and decide where the coins go. So this multisig now, we can define with only a single public key. And again, we gain some bytes, which are crucial in the current blockchain with the scalability issues that we have. This is cool, so this is a nice first step, but the question is, can we do better than that? And then the next thought is that, okay, this is good, but what if we try to put the condition of the payments in the signature itself? So can we encode the conditions that now is used with the hash function? So can we encode that into the signature itself? And the answer is yes. So there's this idea of scriptless scripts that was firstly proposed by Andrew Poelstra. As I said, the idea is to take a condition and encode it in a public key itself, in a digital signature verification. In our work, we formally in our paper, you have a formal description of the protocol, and we formally show that this protocol proposed by Poelstra was actually secure and private, according to our model. The problem here, and also with some of the construction that we have seen today so far, is that they are based on Schnorr or bilinear maps or some other cryptography which is not available in cryptocurrencies today. So one thing that we can do is sit down, wait until they are added to Bitcoin, and then use them. But the question is, what do we do while they are not there, actually, right? So what would be really nice, I think, is that by the time that all these cryptographic constructions don't go into the blockchain, we can employ already the ECDSA signatures or digital signatures, which are already available not only in Bitcoin, but many of the cryptocurrency today. To put in other words, what we are trying to do is, can we realize the idea of scriptless scripts using the ECDSA signatures that we have today in Bitcoin itself? And the problem is that this is challenging. If we not know what easy, I mean, this has been an open problem in the community for a while. And the main challenge is that Schnorr signatures and other constructions have a really nice linear structure. So basically, the randomness are summed together, the keys are summed together. So it has a linear structure. The problem with the ECDSA signature is that it has a really weird structure, not so nice. So it requires inverse of randomness, the x point of a coordinate of a point. It requires the multiplicative shares of the keys, which in practice makes the cryptographic protocol a bit more complicated, but it's actually possible. So in our work, in our paper, we define the protocol and we show that it's actually secure and privacy preserving. And I don't have the time to give you all the details of the protocol, but I'm gonna give you the overall idea. So the first thing that we came up with is how we do a two-party conditional payment using ECDSA itself. And the setup is like this. So we have Alice with a public key and a secret keys in Bitcoin today. We have Bob for the same. And now we try to embed the condition in a public key itself. And the condition says that the payment should only go through if somebody can come up with the signing key associated to the public key of the condition. And the goals that what we need actually is that Alice can create half signature, we saw before, like part of the signature of the payment channel, that Bob can only finish if he managed to get the condition, if he managed to get the secret key for the public key. And the other important point that we need is that, okay, if Bob managed to have such a thing, then Alice should also be able to learn the secret key. Because if you think of the multi-hop payment later, Alice needs the secret key to forward back in order to follow the payment, in order to be able to redeem the coins from the previous user. We will see that in a couple of slides. So this is the setting, and this is how we realize it in a really high-level idea. So what we do is that we create this public key, that AV, that pretty much identifies the two users in the protocol, Alice and Bob. And they jointly create a randomness that not only includes the randomness from Alice and Bob, but also the condition. And this intuitively ensures that they have to use the secret key from Alice, the secret key from Bob, but also the secret key from the condition itself. So both of them know that only when the condition for the public key appears, the final signature will be possible. And then they continue as follows. So Bob gives his 1/3 of the signature, his part of the signature to Alice. Then Alice gives her 1/3 of the signature to Bob. So until this point, we have 2/3 of the signature. The only thing that we need is that Bob learns the secret key associated to the condition. Then obviously he can compute the final 1/3, put everything together, and this is the whole signature. Now either he publishes it in the blockchain to get the coin, so Alice learns it, or Bob just cooperates with Alice, give it to her. And from that, Alice can extract this third part, this sigma C, and from that, it's really trivial for Alice to extract the secret key from the condition itself. And now the question is, okay, this is nice, but how we can use it for multi-hops? How we can use it to actually realize the payment channel network? If you think a little about it, so the first messages look pretty much as the log part, like setting up everything such that Bob in this case will be able to get the payment when he learns the condition. And the second part looks like the release part. As soon as Bob learns the secret, he can get the coin and release the secret to the next one in the path. So this is basically the idea of what we do as a ECDSA-based payment channel network. We concatenate or we chain several of these two-party ECDSA logs. And this is a little example. So what Alice does creates two conditions, the public key of D, and then the public key of D plus the public key of E, and give the secret key of E to Bob. And this is mainly because then Bob is convinced that, okay, I don't know the secret key of D, but as soon as Cat come up with the secret key of D plus E, so the solution for the second condition, Bob can take the secret E, remove it from that secret, and use skd for Alice later. You will see that how it works. And obviously, for the last hop, for the receiver, Alice have to give the condition and also the way to open it, because then only Cat is able to break the condition itself. So once they have this set up, this information, they can just set up the logs from Alice to Bob. It's the same way that we do with the payment channel network, only that now we use our construction based on ECDSA. And again, the nice point here is that these conditions, this public key D and public key E, are totally randomized. They cannot be linked together anymore. They are different, and they cannot be linked between each other. And this is the intuition why this construction gets the security and privacy guarantees that we wanted. And as I said, like once the cat reveals the secret key for D plus E, he can get the secret E from Bob, and then forward the secret D to Alice itself. And this has not only advantages in security and practice, but also in security and privacy, but also in practice. As you can imagine, we can extend this to multiple users. And also reduces transactions for conditional payments. So now we can encode in a single public key, not only the two keys of the participant, but also the condition itself. We have done a little prototype, and we saw that the communication between the users is a little less than 500 bytes. We need some milliseconds for computation. This, please take it with some grain of salt. In the next talk, Connor is going to give way more details about this implementation. But we believe that this actually improves interoperability. So now, instead of requiring that each payment channel actually has a hash function, actually a specific hash function, they need to use ECDSA, which, by the way, they have it. And obviously, it's compatible with Bitcoin today because it's based on this digital signature. So as a summary for this part, this construction improves a little the security, also the privacy, and as I said, the interoperability and the interoperability is greatly improved, and the transaction side is also reduced. So to finalize, obviously I couldn't manage to explain everything that we have here. There is more in our paper. Basically, we show other constructions that not only use ECDSA or Schnorr, but also we show that having what is called one-way homomorphic function suffices to build any construction based, any construction for multi-hop blocks that have security and privacy, as we saw here. We should show that it's possible to combine these locks. So it could be a path that has ECDSA, the next lock is Schnorr, the next lock is these one-way functions, and still the payment goes through with security and privacy. And yeah, as I said, these multi-hop blocks have implemented the Lightning Network. You're going to see more details later. And we believe that this construction allows to have a plethora of applications that we can even think of now, but it will be interesting to get your feedback on that as well. With that, I would like to finish, and thank you for your attention. Thank you very much.
Thank you very much. Any questions? Please do not be shy. Okay. No questions? Okay. Can come to the microphone. Okay.
Let's go there.
I'm not sure if you said this explicitly, but does the your scheme solve the wormhole attack that you described at the beginning of the talk?
Yes, that's a good point. It does solve it because I mean every condition is randomized, is different, and to open each of the hops, you need a secret key which is unique for each of the hops. So if one user in the middle opens, let's say, the sum of n keys, he doesn't know which are the particular ones in the middle. So he doesn't know, for example, which is the ith condition that he could forward it to somebody on the path.
Okay, thanks.
No problem.
Okay, thank you. Some other questions? So your evaluation regarding the privacy concern is based on a particular attack rather than a generalized model of some adversarial models.
So what we have is a formal model of what we mean by privacy, also a formal model of what is attacker capabilities itself. And once you have that model, what we show is an attack against this model, which pretty much shows that the privacy is not achieved. And normally to show that something doesn't achieve privacy, giving an attack suffices.
Yes. So,
Yes.
but very probably the model is, cryptographic models, rather than considering the, say, side channels by
Yeah,
using
it's
traffic analysis and so on.
Yes, no, but in this case, exactly, it's like it's part of the protocol. So this condition is part of the protocol of the multi-hop payment, which is actually what it breaks the notion of privacy. So we don't rely on side channels other than what the protocol defines itself. That's
Okay. If you have one more, I can accept one more. Okay.
Thank you for the presentation. My question is kind of the garbage collection, because if all the scheme is going to the very simple way, it's okay as you presented. But sometimes it's very complex for the real blockchain channel, even the off-chain. In that case, the forward, and sometimes back the transaction, and the garbage will be generated, and some transaction will be the stray transaction, back. In that case, do you think that kind of the garbage collection for that off-chain channel is effective or no?
I'm not sure I fully understand the question, but basically what we are doing here is to take the condition part of the current definition of the Lightning Network, the payment channel network, and change that by our own definition of conditional with the ECDSA. So all the underlying managing of these trust messages or the messages that go off for managing of channels stays the same. So what we do is take this little component, which is the condition, little but still important, which is the condition, and plug it in our own. You're right, like we need all this management of channels, messages, states, but this stays the same. We don't look into that in this project, yes.
Okay, let's thank the speaker again.
Thank you.
Okay, the final talk of this session will be given by Clara from Fromknecht. The talk is entitled Instantiating Scriptless 2P ECDSA, again ECDSA, fungible 2 of 2 multi-signatures for today's Bitcoin. Okay,
All right. Thank you very much. All right, and thank you, Pedro. That was a great introduction to and segue to what I'm talking about. So Pedro gave a very awesome overview of like his work in terms of formalizing multi-hop locks and what that means in terms of like a formal model for the Lightning Network, privacy, and also in developing sort of ECDA scriptless scripts. My talk will be a little more technical and more focused on actually like implementing 2PDSA, demonstrating some benchmarks, and then also sort of like projecting out like what sort of changes might also be necessary to deploy this on like the Lightning Network, and maybe just more generally in terms of you know, progress on the front of Bitcoin. So, all right. To begin, I guess we'll start with a little bit of like history and like how we got here. For what it's worth, these dates are they're rough. We'll put it that way. So Andrew Polsa started work on this. I think he released it in 2016 and proposed sort of like a Schnorr-based scriptless script model. That was really nice because it gave you sort of deniable swaps and the ability to do like cross-chain transfers with the ability without having to like reveal shared data, which in most cases was a payment hash. This actually was able to do that without sort of like revealing the privacy and linking those transactions. He later followed up and provided a construction on how to actually turn this into like a Lightning Network routed a path through the Lightning Network. And that was really interesting. That was something that like at least to me at the time, like I had not known. And really is like the groundwork for where this all ended up. Finally, and like the main win here is that, as Pedro mentioned, like all the sort of payment challenges are randomized at each hop. Both that one asserts that like the payment has to be sort of settled in exactly the order which it. Oh, is that better? All right, my bad. You know, all the payments are settled. It's sort of the reverse order in which they are propagated, and that sort of prevents like the time or the fee siphoning attack that Pedro mentioned. So, like I said, then in late 2017, Yehuda Lindell, which is a very famous cryptographer, published the 2P ECDSA key signing protocol. And it was about this time when I got really interested in this, and I actually started the implementation last October or so. And then it got kind of put on the side for a bit while we were working on other things, and then got picked up this summer. This allows one, as Pedro said, to do a 2 of 2 ECDSA signature, and we don't need to update the base layer. And when I say that, I don't mean like even updating consensus rules. I mean like all the nodes in the network that have been there for the last 3, 4, 5 years, since basically the beginning of Bitcoin, can verify these signatures. And so it's entirely backwards compatible. And the anonymity set is now encompassed by all pay-to-witness key hash, or well, not pay-to-witness key hash, but pay-to-pub key hash or pay-to-witness key hash transactions that exist today, and so they're sort of blend into existing wallet transactions. Later, I think it was April maybe, that Pedro et al. Released the multi-hop lock paper, which formalized the hop-T correlation and also provided the scriptless script-based construction for 2PDSA, which was basically an open question up until then. And show that the two are actually compatible, which is really great because it means that when we actually upgrade from, or when Schnorr actually gets integrated into Bitcoin, we won't have to fork basically the Lightning Network to have both of them be out in the wild. They'll be able to interoperate together, and that will require essentially no changes from the view of the nodes on the network. And that's really exciting because as you start to deploy this, like at some point the network will have to diverge onto this D-log-based payment hash scheme as we migrate away from payment hashes entirely. And so it's better to maybe do that maybe when the network's younger, so we have time to shake out all the kinks and whatnot, and then be able to smoothly transition into Snore whenever that is like fully integrated into the consensus layer. And then finally today we have some working 2PDSA scriptless script code. So that is where we are at this point in terms of implementing this. So at the high level, I'm going to give a rough overview of 2P ECDSA. It's going to be a little technical, but I'm hoping to also like deliver some insight into how the protocol works. It's fairly involved. Uses some like decently heavy crypto, but hopefully like that'll become more obvious to you and like why this protocol is a little complex, but also offers a lot of flexibility on our end in terms of being able to deploy these advanced like D-log-based and scriptless script-based Lightning protocols that Pedro was mentioning. In addition, we'll provide some benchmarks and then later have deployment considerations in respect to like the Lightning Network and how we would go about deploying this. So to begin, I'm just going to show you what a regular ECDSA signature looks like. It can more or less be described in about 5 lines, which is nice. The next 3 slides will be like an abridged version of how to do this in the 2-party setting. So this is just so you guys can kind of grasp like how much more complex this is than just a regular ECDSA signature. So to begin, the 3 links at the bottom, by the way, if you guys are all interested in like learning more about how this works at every level, those 3 papers will be very relevant to doing so. And I encourage you, if you have some extra time, to go and investigate. So the main problem is we have Alice and Bob. Alice will have a private key, little a, and Bob will have a private key, little b. Their public keys are just multiplied by the generator. And now they're jointly going to create a public key q, which is both of their public keys multiplied together times the generator. But neither knows a, b directly. Only each knows little a and little b respectively. But together they'll be able to create a valid ECDSA signature under the joint pub key. For those of you who are looking at this, it might seem a little weird, but they're actually going to be signing under the ECDSH key of A and B, which when I realized that, I was like, oh, that's kind of a little funky. But when you see the ECDSA equation later, it'll kind of make more sense. But yeah, for what it's worth, that's kind of an interesting fact. There are 2 primary algorithms involved when doing 2PDSA. That is Kaizen, which is an offline protocol that is done once to set up the 2 parties' keys. It is fairly involved. It requires an additional crypto system, even in order to get this to the point where you can generate keys and sign. But like I said, it's only executed once. And then there's finally an online signing protocol, which is more efficient, produces a valid signature under Q, and is roughly 2 RTTs for just a regular signature, no scriptless scripts. So okay, here we go. Keygen. Basically, Alice and Bob are going to exchange like their public keys and provide a proof of discrete log that each of them actually knows a secret key to that. So what we use here is a standard Schnorr sig, and that's a non-interactive proof that I actually know the secret key to these pub keys. And for what it's worth, all this stuff is a little abridged, and so mind the notation. Allison generates a Pallier key pair, which again is a different crypto system, sort of related to RSA. And she provides a zero-knowledge proof that the public key is constructed properly, namely that is the product of these 2 large primes, P1 and P2. That'll be very critical to ensure that she can't more or less cheat Bob down the road. Allison encrypts her private key under public key PBK, creating an encryption of it called C, and she's going to send public key, her Pallier public key and C to Bob. Bob is going to store this as part of his final private key, his like 2-party private key, if you will. She'll also provide a zero-knowledge proof that it contains a small value. The Pallier public key is about 248 bits. If you're going to be doing this with a 256-bit EC curve. And so, in fact, like the ciphertext is much, much, much bigger than the actual encrypted value. And so, the implication there is that because Bob only receives the ciphertext, he may not know what the actual size of that underlying value is. So Alice actually needs to prove that it's sort of small, and in fact that it's less than the curve order, the SEC P256K1 in this case, and also that it actually decrypts to a valid pub key and decrypts to Alice's pub key. So that's an interesting little tidbit. But these are all proofs that Lindell actually had to make a new proof for. It's pretty novel and really mixes like 2 different crypto systems. So if you're really interested in like some novel cryptography, I would recommend checking that out. Finally, Bob basically, so Alice does a ton of proving. to generate all these proofs and prove all of this about her private keys and the Pallier pub key. Bob basically receives a bunch of proofs, and then at the end they both compute the sort of the ECDH key, which is Q, by each multiplying their private key times the other's public key. And now the output of this is Alice will save her 2p ECDSA private key, which is just her secret key and the Pallier secret key. Bob then saves the 2p ECDSA private key, which is his secret key, the C, which is, remember, the ciphertext encryption of Alice's private key, and then the Pallier pub key. And that's important because that allows Bob to continue to encrypt messages back to Alice, which she can decrypt. And surprisingly, I just realized this about an hour ago in the audience, you know, because Bob actually has like a ciphertext of C and we have these Pallier keys, it would seem like if I lost these, that they would somehow like basically corrupt maybe a channel if they were dependent on these. But in fact, that's not true, because as long as Alice and Bob say like A and B are derived from an HD seed, they're actually able to then go ahead and like redo the keygen protocol in order to like resurrect the channel. So I thought that was pretty interesting, because I thought that was one sort of downside over this to Schnorr, because typically the Schnorr keys could be derived from HD entirely. But it seems like this is the case, and that that isn't actually a problem for 2p ECDSA, which is kind of nice. All right, so signing. So all of you are probably asking this very question right now. That's a very valid question to ask. And so the main thing is that we can't add public keys and signatures in the same way that we can for Schnorr, because, as Pedro said, they're not linear. And so it doesn't bode well for sort of like non-interactive aggregation, per se. But Pallier ciphertext exhibit partially homomorphic properties. The two specifically are additive. So if I multiply two encryptions of two different messages and then decrypt them, I will get the addition of those two plaintexts. And secondly, you can do scalar multiplication. So if I raise an encryption to like some power and then decrypt it, I will get like that scalar times the original message that's encrypted. And it turns out this is enough to sort of to create a signature under like mostly encrypted data, and then decrypt a nearly valid signature. So, and all of these operations can be done without private knowledge. As you see here, like all the parameters are n, which is the sort of the pub key that Bob keeps around so we can generate more encryptions or do these manipulations. So extracting out the relevant parts of that first slide, the ECDSA signature here is an RS pair, and then you have the S value, which is this K inverse hash of the message, X coordinate times the private key. And we basically need to recreate this, but now instead of the K, there will be two values, one for Alice, one for Bob. And then the X value, there will be two values, one for Bob and one for Alice. So in the sort of like the first step of keygen, they both generate nonces and then prove the discrete logs. Here we're using like Ka and Kb to represent those. Bob then encrypts sort of his inverse times the message and computes this other value, which is the inverse of his nonce times the X coordinate of the aggregate nonce, and then times his private key. Now the interesting thing here is he can then, this part in bold, where he actually is combining a ciphertext and manipulating them using the transformations up above. And then I have highlighted here in basically color code what the purple means both parties are aware of this value. The blue represents Bob only knowing this value, and the red represents Alice knowing this value. So just knowing, so all Bob really had at the beginning was this little a in an encrypted form, and he's actually able to manipulate this value into what we have here that's actually encrypted. And he sends it back to Alice. Alice is able to then decrypt it and multiply by her the inverse of her nonce. And that generates the full signature. And if you compare this to the equation above, it's sort of like the simple ECDSA protocol. Wherever there's a K, it's replaced by sort of an Alice and a Bob K. And then similarly, the secret keys are also like Alice and Bob replace the single secret key there. So you can see that these equations are similar enough, and this actually works as an ECDSA signature. The final step is making sure that the S value is small. So now the scriptless script signing is very similar. It requires an extra round trip to actually do this little transformation and extract the secret data. But for the most part, the protocols are very simple very similar at the implementation level. So I'll kind of like omit the details there. But if you're interested, those are detailed more in Pedro's paper. So now let's look at some benchmarks. For what it's worth, so yeah, let's see. These were computed last night. For what it's worth, I've been kind of like optimizing over the last week, like on the flight and stuff. So like this is about. I tried to get the keygen under 1 second, but time permitting. So, but overall, 1 second is for keygen, actually, I was pretty surprised at. I kind of thought it'd be slower, given all of the actual like crypto and complexity of the keygen protocol. And I think this is very promising because I think even here, probably the slowest thing is use of Golang's BigInt library, which is notoriously like not constant time and you know, has other issues in terms of like memory performance. So I really think that like that could even be driven down maybe by like 2 to 5 to 10x ish, but we'll see. We're going to continue working on that. Signing, as you can see, is like under 30 milliseconds. That's pretty huge. I think as far as like an online protocol, that works pretty well. And then, yeah, and then also in basically testing, the signing and the scriptless signing are actually very consistent in terms of just their allocations, time, and basically numbers across the board, which I think is very promising because ideally we'd like to get those as close to constant time as possible. But, you know, that's a lot of optimization work. So for what it's worth, these were tested on my laptop. You know, some constraints here is that this is all single process. There was no network latency, no serialization. This is basically a straight computation of the work involved. It used a non-interactive discrete log proof, proof of knowledge, and proof of the Pallier correctness. The Pallier range proof, where you actually prove that it's a small value and that it decrypts to a proper ECDSA pub key, we're still interactive, but the Pallier range proof should be possible to make non-interactive, just needs a little more work. And then the Golang, so I have Golang code that'll be published there probably today, tomorrow. It was like 1.7 lines of fairly tedious code, so but it will be available for anyone to try out. There's concurrent work being done by Omer Shlivitz and Gary Benatar. And that's also, I have the link for the repo there. And they're also working on interesting T-event construction for this ECDSA key signing, which I think there might be a paper coming out soon, I'm not sure, but that'll be definitely something to check out because, you know, I mean, I don't know anything that does anything close to that, so it would be nice. And all right, so now let's go into sort of like the modifications that you need to actually deploy this on the Lightning Network. So with just 2PDSA and Schnorr, no scriptless scripts, these are sort of the requirements that we need to change. It's sort of like script changes. Funding outputs, they're currently like 2 multi-sigs, and obviously to spend that you need a signature from each party. And the cases in which this is relevant is cooperative closes. So when both parties agree to basically close out the channel, and this is they're not unilaterally closing in the sense where the contracts are actually executed, they just kind of close out and split the balance however it was allocated before. And the other is when a commitment transaction goes to chain, this is when either side force closes. Those transactions are pre-signed, so basically in the update protocol, that is in the offline update protocol in Lightning, there you need a 2 multi-signatures to update these commitment transactions and HTLC outputs. But all of this can be replaced with a single pay-to-witness key hash linking output, which is nice. It saves space, and it has like improved privacy. HTLC outputs, they use 2 multi-sig and non-standard HTLC scripts. Basically, there are 2 types of HTLC scripts that we use in Lightning. There's what's called an offered and a received HTLC script. They're mostly similar. It just depends on sort of like which direction the HTLC is flowing across the channel. And both require a 2 signature to spend if it happens to be like an offered timeout that happens or a received success. Those are in essence sort of like the worst case in terms of space in the way that it manifests on chain. And this can be replaced, the whole HTLC contract can be replaced with like a much simpler script, which I think is a big win. As you'll see later, I have a slide that kind of demonstrates this. And finally, some improvements with actually scriptless 2PDSA and Schnorr. We can finally remove payment hashes. They're no longer necessary. And then similarly, we can remove pre-images from the witness. So right there, you're saving easily like 52 bytes in many of the witnesses. So I think those are pretty big wins. Just in terms of space savings, those are fee improvements, and ultimately like less load on the blockchain as well. So, which is kind of the whole point of this conference. So now just like kind of diagramming out like what this would look like for funding outputs. You know, have like regular 2 multi-sigs, Schnorr 2 multi-sigs, ECDSA ones. The reason I have pay-to-witness key hash at the bottom is just to highlight that the 2P ECDSA multi-sigs are virtually identical to on-chain. Those are basically indistinguishable. They will look like random pub keys altogether. And then obviously the space improvement here is roughly halved, which makes sense. You know, what was 2 keys is now 1 key, and what was 2 signatures is now 1 signature. And one note is that for unadvertised channels, this is a pretty huge privacy win. So if you're a Lightning channel and you're actually going to like advertise that I am like a routable node in the Lightning network, you're already sort of giving up privacy on that output. Like people know and can verify that you are a channel and that belongs to you. But if you're actually a private channel, or what we call like a non-advertised channel, this gives you a huge win in terms of privacy. Because funding transactions now look like regular pay-to-witness key hash transactions. So I can open and cooperatively close channels virtually indistinguishably from just making a random payment on chain. And I think that's a pretty huge win, especially as we move to a network where many of the like mobile devices or a node you keep on your laptop is not going to advertise its channels at all for routing because of its sort of like intermittent connectivity. And finally, there's actually less bandwidth at the gossip layer due to the channel announcements now having like one less signature. So that just sort of improves the network load in general. HTLC scripts. This is an HTLC received. This is a received HTLC witness script. You're probably looking at this and thinking, oh shit. Because, I mean, honestly, it's very hard to reason about. When you're having to do like flipping pub keys and verifying time locks, that's totally acceptable. So what we can do with this is make a much simpler script, which is, it just has a revocation clause, a timeout clause, and a success clause. All of them are governed essentially by a single signature. And really the only thing that differs in all these clauses is that the timeout clause has the explicit CLTV parameter. But other than that, they're virtually identical. What this does off the bat is a 20% reduction in the script size. And that is of basically all, when you spend any HTLC outputs on a commitment transaction, that is a 20% reduction in the witness script size. Like I said, it improves the readability of the script because it becomes very simple to actually reason about what things are happening here. Now, in terms of witness sizes, I picked the received HTLC script size because it basically highlights the worst case in terms of like the amount of space at the moment that's required on chain for settling unilateral transactions or for closing channels unilaterally. So we actually see a 78% reduction in the success witness size, and that's because we switched from we removed a payment like a payment preimage and pub key, or sorry, we removed a signature, a pub key, and a payment hash and preimage. Which ends up being pretty massive. The revocation witness is now only is 30% smaller. The timeout witness stays roughly the same. It's just a single signature. And you can expect roughly similar improvements from the offered HTLC script, but generally it'll be a little bit smaller overall on kind of all these metrics, but still very similar. Now this part I think is really interesting. Channels are obviously bidirectional, right? Right now in the protocol, when I'm trying to forward an HTLC, I sort of send to the other node like all the parameters for the updates in which that the HTLCs have, payment hashes, time locks, amounts, and the other channel applies all those updates, and then I send a batch of signatures covering all the outputs that I just sort of like created on their commitment transaction. If you notice from Pedro's talk and maybe earlier, when you do these 2P ECDSA signatures, only one party ends up with the signature. And it like typically with a normal like script multi-sig where you actually have like Alice's pub key, Bob's pub key, and then two signatures, each can sort of contribute theirs independently. And that actually simplifies things in some respect. So what you have here is you have a funding output that is secured, or that is locked with a single output on chain. And to actually be able to spend from this, and to have either party be able to sort of initiate this ability to sign, you're going to set up two instances of a 2P ECDSA key pair, so that either party can go ahead and update this. And that will allow them to sign commitment transactions that spend from this output. Or similarly, either party could initiate a cooperative close of the channel. In addition, HLC outputs will also have like a static key pair, but these will actually use different keys. And it's not important that they're the same one because the actual, it's only important in the funding output case that they're the same because it's actually spending from the same output. Here on this case where we have the timeout success transaction spending from the HLC outputs, they can actually differ. Some of you I know are probably going to ask, like, how does this apply to L2? You'd still need four overall total instances of 2P ECDSA here. But on the sort of like commitment transaction level, you'd only they would share one key, which for what it's worth. So it's roughly about the same, but overall that does kind of factor in. So all right. So moving on to onion packets and how this affects onion routing. So this is the current bolt 4 onion packet structure. So this is what my view looks like when I decrypt an onion packet I'm able to read right now this sort of realm byte, this per hop data, and then there's a 32-byte MAC covering everything. And then there's a bunch of like random bytes at the end that are like authenticated and encrypted, but I can't read because they sort of get like shifted around every time the next person decrypts and I forward. So what's going to change here is the data that's stored in the per hop payload, and then obviously like there's the green parts are what are affected by the size of that. In the current per hop payload, we have just it's about 32 bytes. The new one includes basically a pub key, a Schnorr signature, for example, and then a 32-byte sort of secret key, if you will, and that's the difference between like the incoming and the outgoing locks that Pedro was describing. And so you do get a roughly, the overall onion packet size grows by about 3x. Fortunately, when you're constructing and decrypting these, the majority of the bottleneck in terms of like computation is all in asymmetric crypto operations. And those are used to derive just sort of like ephemeral keys and blinding factors for each hop along the way. And this scales linearly in the number of hops, which is something that I worked on back in February, getting that down from quadratic. And then, so basically the end result here is that this will have very little impact. I'm projecting, obviously, but this should have very little impact on the actual like performance of construction and decryption of these packets, because those operations, or expanding the size is only relevant, excuse me, expanding the size isn't that relevant because we still have the same number of hops, but all the data is encrypted with symmetric encryption, so it should stay relatively performant. And yeah, finally, so I was just gonna like go over some of the advantages that we have here of this technology. I think it's really fascinating. So the main advantages I see are obviously like it can be deployed today. I may or may not have done this on mainnet, but none of you will ever know because of the privacy wins. We obviously get smaller scripts and witnesses, which translates directly to lower fees. There's the increased on-chain privacy via the increased anonymity set for funding outputs. And for what it's worth, this privacy, well, really all of the talk that I've described today has more or less equal analogs into the Schnorr world. I think the only real difference at the time today is that the 2P CDSA blends into all existing traffic, whereas if you start with Schnorr, there's going to be a smaller anonymity set. That being said, I think there's a future world where most transactions migrate to Schnorr, and so as that time comes, then it would be like, you know, a user may choose to actually switch over to Schnorr just for the privacy benefits, for example. But that's really the only immediate win, apart from also being like much more performant and less complex. You also get like real proofs of payment, because I now get like a secret key back that I can sign with and prove that I paid a particular invoice, something that I refer to as invoice tunneling. And you know, some more work being done in this area. I know Pedro's working on it. Some of the disadvantages obviously is just complexity. I mean, this took about a year start to finish to implement. Well, obviously not full time, but you know, it is a lot of work and takes a lot of careful amount of like just analyzing how all these things behave. And also, you know, on a mobile device, this may not be the most practical protocol. We'll see how far we can get in terms of like efficiency in that front, because also maybe you don't have as many cores just to like do all these proofs in parallel. And the really only other downside is that it takes more updates to update a commitment transaction. You're gonna have more round trips there, so that could be perceived as more latency. However, it does seem possible to sort of pipeline the signing protocols such that you can shave off a round trip at the very least, and maybe more, but we're gonna leave that for future work, so. Thank you very much.
Okay, thank you very much. Okay, do you have any questions? Don't be shy. Okay, no questions? Okay, in your performance evaluation, you know, I think in the case of these DSA and Schnorr and sort of things, depending on the implementation of Nancy's, we can, or the signers can use some pre-computation.
Yes.
Yeah. How do you assume regarding that aspect in your test?
Exactly what you said. In signing, you can sort of have like maybe pre-committed nonces. Maybe those are derived in sort of the same fashion that revocation keys are today, where there's sort of like a root seed, and then in that sense, all the nonces that you'll eventually sign for are pre-committed to. And then so there's, you don't have to do this extra like round trip just to prove that the nonces are valid. So exactly, that would be like one obvious way in which you would then optimize signing. So in that case, the round trips then drop to somewhere between like the number of round trips drop to maybe like 1 or 2 in terms of signing. which I think would be a big win. And then there's also the possibility of pipelining those messages on top of existing Lightning Protocol messages and just sort of the flow that takes when doing the update. And so hopefully we can get that down, and I think that'll be something that we study probably in the next couple months.
Okay. Any questions? If you have one, I can accept one more. If nothing, it's already time is approaching, and let's thank the speaker again, and let's conclude this session. Thank you very much.
Thank you.
Okay, so we'll take a quick 15-minute break, and when we resume according to schedule at 5:20. 少し15分の休憩を取ります。続きまして、続きのセッションは5時20分からです。